Okay, so yeah, sorry about the technical difficulty. Yeah, so they say that they are going to record everything, right? So yeah, so everything that I'm going to say is after the censorship. Okay, yeah. So today we are going to talk about maybe a little bit less AI compared to many talks that has been given before, but more like data science. So we work on, as you can see, that road traffic forecasting. So when the time that we began to work on this topic, and actually we never feel like we can do a lot of improvement, because as you can imagine that a lot of people work on the road traffic forecasting for quite a while, maybe it could be more than a few decades, right? So, but still that we find something that we may have some idea to keep improve the result. So here is the thing that I'm going to share with you. So the work is actually work with two of my students, Alex and Junjia. Okay, so we have been working on road traffic forecasting for a few, maybe 2 years. And actually, these few years, we work on IoT analytics. As you can see that for the transportation, for smart environment, etc., right? So we can usually just use the sensory data and analyze the sensory data, and we can find something. Maybe we can have a better way to predict the future in some sense. So all the things that underneath that we want to build a so-called smart continuous sensing monitoring foundation. So if we compare to the traditional machine learning methods, that is instead of just build one model, actually we build a series of models. As time goes by, the model should keep improve, and also as you can see that it's a line way that we continuously to collect more and more data, and the model should be adjusted automatically. Okay, so given that this foundation, that what we need to do is that we need to do some online pre-processing, and also everything must be considered real time in some sense. So which means that if we're dealing with a lot of data, later I'm going to show you that for the traffic data, sometimes we can work on the more than just a few years of data. And to consider everything at once, we need to make sure the speed is like acceptable. Okay, so to work on IoT data analytics, from time to time, we are going to talk about, let's say, if we work on this one sensor, okay, so which is the time series data. If we work on a lot of sensors, but just one moment, then we have a spatial modeling, right? So to combine both, then we have a spatial template modeling. So this kind of modeling has been, again, discussed, studied for a while, but we try to give some more improvement based on some intuition. Okay, so traffic forecasting, of course, is very important, right? For personally, we need this kind of information for decision making, right? Such as, okay, when to depart, when to leave our house, or maybe between, let's say, drive our own car or take the public transportation, we need to make a choice, right? So for the government or the city designers, they also need this kind of information to control the traffic lights and also to design new road. Yeah, so the factor to decide the road traffic is very easy to understand, that the time and location, that is very important, right? So such as rush hour, non-rush hour, the location, if it's close to a city center, there'll be always rush hour, right, in some sense. And also the weather, and also some other like a road construction or maybe accidents, right? So specifically, we can also consider such as if we have personal information, then we can distinguish between, that's experienced driver and non-experienced driver. So from time to time, I always think of that the Google Map give us some solution, right? If we want to go from A to B, right? And if we consider myself as a like experienced driver, then maybe I want to know the time is like, instead of just mean value, right? Actually, we want value with certain variance, right? Which means that from A to B, most people try like 1 hour, but some people try 1 hour, 10 minutes, and some people try 50 minutes. So I know what I'm going to expect instead of just give us the mean value. Okay, so how to give us a better prediction? Actually, we try the data-oriented approach. And in this data-oriented approach, what to consider is that some kind of long-term and short-term factors if we consider the time temporal domain. And on the other hand, we also consider the spatial domain and something else. So I'm going to explain that in a few minutes. So given this data, right, so as you can see that it's a traffic data along a whole week, right? The Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday, right? I mean, people in Taiwan, they are going to easily understand that this data is not from Taiwan, because as you can see that there's a traffic rush hour in the afternoon, right? Most of the day, right? But in Taiwan, there's no rush hour in the afternoon. You know why? Because at that time, people are still working, right? So, yeah, so there's no rush hour. So, yeah, so actually, in Taiwan, if you want to know, it's almost like the more traffic in the morning rather than in the afternoon, right? So it could be that we switch between the morning and the afternoon. That'll be more like the Taiwan's data. But actually, we work on the data from US highway, because they have been collecting the data for more than decades, like more than 10 or 20 years. So as you can see that we can work on big data, right? So given this data, we work on, let's say, periodic patterns. As you can see that for IoT and a lot of IoT data, some data could be related to human activities, right? Some data are not. If we talk about the data related to human activities, then we have to consider the daily and weekly patterns like that. So that's highly influenced by human activity, as you can see. And so that we have to consider those periodic patterns and also some noise. And some noise means like, okay, maybe sometimes even that most of the day, the pattern looks like quite the same, but sometimes they're just an accident. So that as you can see that the traffic data, usually there will have a lot of accidents like this that will heavily influence the result. Okay, and if we consider the different days, right? So we have different, maybe similar pattern if we talk about weekday, and for the weekend, there could be something different, right? And also, if we talk about the different locations, right, for the different sensors, it looks like they are similar, right? Especially if you know the transportation, then actually the downstream sensor will influence something happen in the upstream. Okay, so this slide is to summarize what we are going to consider in the data, right? The traffic data, we have a temporal and spatial consideration, and also for the temporal part, we have long-term, short-term patterns, okay? And for the spatial pattern, then we consider neighborhood sensors, and also we consider some other information. Sometimes we can consider weather, but we don't include the weather in this work. Okay, so the problem is very simple. We just given some historical data, we want to predict the future, right? So it looks like quite easy to understand. So, but the thing is that the data could be quite large, right? So sometimes if we want to feed in all the data in the history, right? So to predict the future could be very heavy. Actually, we are going to explain that we don't need a lot of data. We just need part of the data, and we can still have the almost like the same prediction. Okay, so the issue we have already explained most of that. We want to deal with periodic pattern. Actually, the more recent result is that we don't need the information like weekly or daily periodicity, and we can detect that from the data automatically. Okay, and also we consider unsuspected pattern, that means the short-term pattern, and something else. okay, like the for different sensors and also for different features, like for the traffic data, we usually consider instead of traffic speed, right? And also we consider the flow and occupancy, etc. Okay, so what is the method? The method, before we go on to talk about the method, let's just talk about the data first. So the data, and just like many IoT data, usually we can explain, we can express in this way. So we have some core data, like whatever information that we can collect on one sensor. But when we collect that data, we also have the location stamp and the time stamp, okay, along the side. So combine everything together, so one data could be like this, the core data, and also with the spatial and temporal information, okay? So if we want more efficient models, then usually we want to do some data aggregation, right? So just like if usually the sensory data could be a lot of, the sampling rate could be too high, right? In some sense that in certain situation that we can just aggregate a few data together and combine into one, depends on how model can afford, the computation can afford. Okay, so here's one easy illustration to say how to collect all the data, right? Suppose what we want to predict is right here, right? So we want to collect some short-term data, right, with a higher sampling rate. We also want to collect the long-term data with lower sampling rate and combine together. Here we just say try some very naive way, right, to use the uniform sampling rate for the long-term data and the uniform sampling rate for the short-term data and combine. Okay, but a more advanced way, you can like try some aging effect, right? Gradually increase the sampling rate. But later I'm going to show you that even that we just use this such a naive way, the result could be good, quite good. Okay, so we combine two parts. Here is the long-term data, here is the short-term data like this. Okay, so here's the framework. We have some data coming, and the data could be considered a part of the training data, okay? Then given that limited buffer, right? And then once the data is, could be like the buffer is full, then we consider data could, the old data could be expired, right? On the other hand, we also need to take on consideration like when the model should be keep improved or keep adjusted according to the new data coming, right? So when there'll be some new data coming, then we return our model and build a new model for the prediction in the next moment. Okay, so here is some consideration if we consider the so-called Motty periodicity. So if we have just the time and the space, right? So usually the model, people try like ARIMA, etc., right? And then we have the result. But what we want to emphasize is that for given such a like IoT analytics, IoT applications, from time to time we have a periodicity like daily, weekly periodicity, right? So we want to consider this in our modeling. So how to do that? So consider that the raw data could be like this, right? And raw data could be like the X, the core data with the spatial and temporal information, right? And that if we focus on the temporal data, if we focus on the time information, then we can say, okay, the time information, just consider that's absolute time, right? And actually, we also consider a lot of times, like, okay, time in a day, time in a week, etc., right? Maybe time in a year. So how to do that is like we take the raw time information and we compute the quotient space of the time, okay, given many different kinds of periodicity. Then we have such data after the preprocessing, like the core data, spatial information, and time information. Time information, when we have a lot of periodicities, then maybe we can consider time in a day, time in a week, etc., right? So there'll be a lot of times to consider in this case. Looks like quite naive to do, right? So, okay, So we have given a lot of periodicity information. We can have two choices, like, okay, we consider many times in our model at once, or we consider, let's say, for different single periodicity model, okay, then do the prediction and combine. And actually, this way is better based on our experiments. Okay, so then up to now, we didn't say what to do, the methodology, right? So what we try is the Gaussian process. Gaussian process, to give you some short introduction, is like we are given some data, and then we work on the functional space, which means that a lot of functions given the same mean and the variance, then we can fit to this input, okay? So as you can see that different lines means a different function. They can all fit into the input. But what we want is to compute the average of all these functions, okay? That could be our prediction. So here is the prediction, right? So given, first of all, a Gaussian process to define a Gaussian process, we need a mean function, and also we need covariance function. Covariance function is to define the relationship between 2 points when they are not in the same location, right? So here is the covariance matrix, the inverse of covariance matrix. Here is to compute the difference between 2 points, okay? And then in the end, when we have a new data coming, then we want to predict the what to predict is based on this formulation. So the first part is the mean function. The second part is the covariance. So if we focus on the first part, the mean function is mainly used for our prediction. So as you can see that, so here the big X means all the historical data, and Y will be the value that we want to predict, right? Okay, so you can imagine that those X and Y will be quite large, right? And then we want to give one new X, we want to predict Y. So that's the thing that we work on. Okay, so here we can see that in the formulation, we need to compute such a big, the inverse of big matrix, right? So given that historical data could be quite a lot. Okay, so how to do that? Okay, so of course, we don't want to compute the matrix inverse directly, right? So we want to make the matrix to be as small as possible. So that's why we do some aggregation on the long-term pattern, long-term data, and combine with the little shortened data together, then we can have quite a good result. Okay, so this part I'm going to skip. The parameter tuning means like maybe people consider the Gaussian process, and for instance, the support vector regression could be somehow similar to each other, but actually there's something different in the sense that the Gaussian process, first of all, if we work on the time domain, right, so we can use whatever parameter used for this moment and to predict the future, right, which means that what the strategy that we use now in this work is that we use the parameter for this moment to predict the future, and then when we receive more data in the next moment, we adjust the model parameters according to the new data coming. So that's the so-called automatic relevance determination, this strategy. Okay, so here comes the evaluation. How much time? Yeah, okay. So we work on the data collected in the San Diego highway. So as you can see that they provide yearly data, but we just work on just 1 year data and to see how the performance is, okay? So we have actually if we work on the raw data is the time, location, and the occupancy flow and speed, right? The speed is the thing that we're going to predict, okay? So as you can, we have discussed that for the time information, we have make it to be, transform it to be considering, let's say, different periodicity, means like time in a day, time in a week, etc., are all considered as the data input. So that's a prediction we used along the highway. We predict the traffic in those 5 different locations, okay? So here's the result. Imagine that we consider the temporal information, spatial information, etc., right? So we're going to show you the result according to different aspects. So here, that's the first thing that we want to check the prediction. If we see along, let's say here will be, I hope that you can see the numbers from the day 1, day 2, up to day 14, right? So when we are given more and more data, let's say the historical data, okay, as you can see that after we collect 7 days data, then the things started to get more interesting, right? So the performance, the MAE, mean absolute error will keep decreasing, right? So then after the 7 days, the data, the error looks like stabilized, as you can see that most of the time, right? And for the Sunday, Saturday, Sunday could be quite easy, right? Because we don't have a lot of traffic or rush hour, which means that the traffic is easier to predict. So that's we actually consider the daily model, right? So if we just keep the time in a day, right? So that's the result. If we work on time in a week, right? Actually, that's the result. We have the 1 week, 2 weeks, up to 4 weeks, right? So we have the result. As you can see that the performance looks like quite stabilized, right? So which means that when we have a 1 week result, that will be good enough most of the time. And we can also compare between the daily model and the weekly model. On the left-hand side, we just use the daily information, means that we just consider the daily periodicity. And here we consider only the weekly periodicity. And as you can see that the weekly periodicity works better than the daily periodicity. Here is to combine daily and weekly together, then we have this. So that the MAE is mile per hour result. So 2 miles per hour looks like okay, right? Not yet. Actually, we up to now we just consider this part. We only consider long-term factors. Okay. If we also consider the short-term data, we can keep improve the result. Okay. When we get 10 minutes or 20 minutes or up to 2 hours more data, as you can see that 20 minutes, 30 minutes more could be enough to have a very good result. Here the MAE is keep decreased to 1.4 something mile per hour. Okay, so here is the summary, right? We consider different kinds of modeling when we consider the single periodicity or consider multi-periodicity. And when we combine multi-periodicity together and as well as the short-term pattern, then we have the best result here. Okay, so just to take a few moments, and we also consider the spatial information such as we combine many information from different sensors together, we can have better result. And also just like here, so we can include, let's say 1, 2, or 3 sensors in the downstream. Of course, we can have better result. Here is to consider some other information like occupancy and the flow, then we have a better result. Okay, but if we just focus on the temporal, spatial, and temporal, the temporal information, the result is like this. Here is the result to compare to support vector regression. Okay, the same, almost the same design, right? So as you can see, the support vector regression doesn't perform as good as our Gaussian process-based model. Okay, everything just a little bit worse. Okay, and due to the time constraint, then I just want to compare some other methods, such as to consider the ARIMA and also vector ARIMA. So here's the result. Just here, we want to emphasize that the traffic data, if we consider the short-term and long-term data together, right, usually it won't be like the uniform sampling rate, which means that if we want to use ARIMA or things like that, or if we want to use a hidden mark model, it won't be that appropriate in this case. So that's why they don't perform so well. Actually, how to get this result is just we feed in all the data, right? As you can imagine that it won't be very efficient. On the other hand, we compare to many other methods. So, we summarize all the comparison in this way. So between the server-rated regression, ARIMA, and also our approach, okay? And also, this Zeus approach is some kind of a spatial temporal modeling combined with different ARIMA model together, and they perform quite well, but we can do better. And also, we compare to other different approach like a sensor completion, and also these days, right? People need to talk about deep learning. For the tensor completion, we have better result right here. Actually, what we want to emphasize is that the comparison these days is not that easy in the sense that people may say, okay, if we want to implement their method, we may not implement 100% correct, or maybe we don't use the same parameters, etc. Right? So, so that's why we actually quote the numbers from their work, and also we use the same data they use and try our method, and we can do better. And also, this one is the network-based comparison, network-based approach. Even that they don't really try like a deep network in some sense. They try some shallow network, okay? But we can do better. We don't want to say these days, right? People tend not to say we can beat deep model, right? So we don't say that, right? Okay. So, but at least that we have some competitive result if they don't try a lot of deep a lot of layers. Okay. Conclusion. So we propose we call that even that we have some superior result to many existing state-of-the-art approach, we still want to say, okay, we just try to give some baseline model so that people maybe starting from now can compare to our approach and to see if they can do better, right? For instance, maybe by deep learning, right? And the difference that we try, there are two things. One is that we try Gaussian process to be the base model for all kinds of prediction. The second one is that we consider different periodicity, okay, in the long-term data, so that usually looks like quite naive, but when people really try it, right, so the result could be better. Okay, so that concludes my talk. Yep.
So Professor Pao, I have a question is that I just saw your experiment result you predict like using about a weekly data with the Monday to Sunday, but there's I think there will be a exclusive situation is that in the long-term holidays, such as in Taiwan we have Chinese New Year holidays, and the traffic will be really big traffic jam problem. And I think, I have a question is, will you do another experiment about the situation of the long-term holidays?
Yes, yeah. So actually, we try to propose a generic model, right? So which means that if you have more data, if the machine can compute that such a big data, right? We can try the time in a year, right? Which means that up to now we don't have a lot of yearly data, right? We only have a few years. If we have, let's say, maybe 5 years, for instance, right? So we can really try it, right? To see, right? For the US, maybe we need to consider the Christmas, right? There will be different traffic condition, right? So, but we think that it's hard to really predict such like a spatial event, really, right? But if we need to have data, right? So if we have a lot of historical data about the same big event, maybe we can do something.
Thank you.
Thank you.